Guys, welcome to the world of quantum chemistry. In this video, I'm going to discuss about the origin of quantum chemistry and its introduction. Before the evolution of quantum chemistry and stuff, the first evolved one was the classical theory of the classical mechanics. Okay, according to classical mechanics, light is an electromagnetic wave composed of continuous wavelength that form a spectrum. Okay, this theory they propose that intensity is proportional to the square of the frequency. Okay, that is a relation just like y equal to x square. Okay, it increases exponentially, but the experimental value is not observed like that. The experimental value is given as the dark line in the graph. Okay, and thus we can conclude that the classical theory is wrong. And also there were many things that were not able to be explained by the classical theory. Okay, classical mechanics can only deal with the low energy part of emission, that is ultraviolet catastrophe. Okay, classical mechanics predicted the light emitted continuously, but Max Planck later discovered that light is emitted as small particles discontinuously called quanta or photons. Okay, and also no electrons are emitted unless it is above a certain cutoff frequency. Okay, the maximum kinetic energy of photoelectron is independent of light intensity, and also the kinetic energy increases with increasing frequency. So we can definitely rule out the classical mechanics because here there is no relationship with the kinetic energy to the intensity, and also the kinetic energy increases only according to the frequency. So we can just say that energy is proportional to frequency. We cannot talk about intensity here. Electrons are emitted from the surface almost instantaneously, even at low intensities. The only thing that matters is the frequency. Okay, we'll discuss that about in the coming slides. Okay, photoelectric effect. Okay, that's very important. Okay, consider an initial light of frequency nu heat a metal surface, and also an electron is emitted from the metal surface instantaneously with a kinetic energy T. Okay, but there is a case here. The incident light should at least have a minimum frequency, that is nu 0. Okay, so the energy is h nu 0, that is the work function. The certain metal surface has certain work function. Okay, consider the case here the nu is greater than nu 0, so that is why an electron is emitted. Only the electron is emitted only if the frequency is greater than the cutoff frequency nu 0. Okay, and the kinetic energy increases linearly according to the equation. Here the kinetic energy, we can write it as equation also. Kinetic energy is equal to h nu minus work function, or kinetic energy is equal to h nu minus h nu 0. Okay, here we are considering the case of a potassium metal whose work function is 2 electron volt. Okay, if the energy is below 2 electron volt, no electron is emitted. If the energy is 2 electron volt, an electron is emitted with no kinetic energy. If the energy is greater than 2 electron volt, the electron is emitted with a certain kinetic energy value. Okay, I think you are clear with that. Okay, next we will come to the most important part of this section, black body radiation. Okay, according to black body radiation, okay, the first case we are hearing about is energy is inversely proportional to wavelength. Okay, for low wavelength we can get high energy, And as the temperature increases, in this graph you can note that as the temperature increases, the curve smoothness decreases gradually. Yes, it's very clear. The curve smoothness decreases with increase in temperature. As the temperature increases, the peak moves to shorter wavelength. You can observe that at high temperature, the peak, the maximum value of the graph, will move to lower wavelength or towards higher energy, as energy is inversely proportional to wavelength. Okay, that is a very important point. You must note that. I will tell it once more. Okay, as the temperature increases, the peak moves to shorter wavelength. You can note that the visible part is from blue light to red light, as the frequency red light has higher wavelength than blue. Okay, as the wavelength increases, yes, okay, the peak, as the temperature increases, the peak moves to shorter wavelength, that is towards blue light from red light. Okay, that's very important. That's the reason why a very hot object, when it's heated up again and again and again, finally when it attains a very large temperature, that is above 5000 Kelvin, it will shift towards blue color. Okay, which will indicate a very high temperature, and the peak had moved to a shorter wavelength. We can also see that for higher wavelength of light, there is a slow decay for no emission independent of temperature. That's also important. The peak becomes very sharp at high temperature. Okay, that can be noted easily. The total energy emitted is also directly proportional to the area under the graph. That's very important. The total energy emitted is directly proportional to area under the graph. Okay. Next, we will come to the de Broglie wavelength relation. What are the things that lead to the de Broglie wavelength equation? Okay. According to Einstein, the energy of a photon, energy of light, E is equal to mc square, or E is equal to momentum into c. Momentum is nothing but mc into c for a photon. Okay, and according to the modern Max Planck theory, energy is equal to h nu. E is equal to h nu, or E is equal to hc by lambda, which is equal to the same energy as the Einstein's E equal to mc square. So we can equate these two equations. hc by lambda is equal to mc square. So we can cut the c's from there, and we can finally get the equation lambda is equal to h by mv, h by mc, or h by p. We can also say that this is the equation for light. If for a matter, another particle, we can write is lambda equal to h by mv, or lambda is equal to h by p. I hope you like my video. If you like it, please subscribe to my channel for the latest quantum chemistry updates. Soon I'm going to upload more videos related to quantum chemistry. I hope you're thorough with this course. Thank you.